higher level. Now I invite Dr. Devabrata Datta to take the chair for the next talk to be delivered by Professor Sunil J. John from NIT Calicut.
Professor
So,
Som, I
Dr.
take
Datta.
leave because I am now in Calcutta, my old city. So I'll just go out. I'll just take leave. Thank you.
Okay, thank you.
Sir, please introduce. Your mic is mute. Unmute your mic. Unmute your mic.
Yeah. Am I audible now?
Yes, yes.
Yeah. So whether it's Sunil Jacob John's biodata is with me, because I have to have the biodata like Professor Samarjit Kaur.
Yeah, just wait.
Just to send the CV to me, I can just do
That is there in your mail. Just wait.
it. Is it there now? Hello?
Yes, you please see in your WhatsApp.
Okay. WhatsApp, okay.
Yeah.
Okay.
It is there also in your mail, but
Okay. WhatsApp. Professor Samarjit Kaur is there. Oh,
sorry.
no,
This is...
that is, it is Professor Samarjit Kaur again in the WhatsApp. So you send the... both the time Samarjit Kaur has come.
Okay. There was an error. There was an error. I'm sending it.
John sir, please wait. Let me introduce you.
Oh, don't worry, sir. Don't worry.
Yeah,
You
yeah.
take your own time.
Yeah. No. It will be just...
If you want, I can introduce myself and start also. No problem.
Sir, is it ready now? Otherwise, I will, whatever I know about him, that I will tell, and remaining part he himself will tell.
I have already mailed you, sir.
Okay. Mailed me.
Yeah,
Okay.
I'm just going to paste in your WhatsApp.
WhatsApp.
Yeah, that will be easy to open.
Okay, I have got that. No necessity. Okay. So, good afternoon to everybody. Again, that will be continuing the previous session. It is my again proud privilege to introduce Professor Sunil Jacob John. He is currently a professor of mathematics at NIT Calicut. He has also served the same department as HOD from 2017 to 2019. He completed his PhD from Department of Mathematics, Cochin University of Science and Technology. His area of interest includes topology, set generalization, soft computing. He has published more than 60 journal articles, 5 book chapters, and 6 books. He has supervised 13 PhD students and at present 6 PhD students are working under his guidance. In addition to that, I would like to mention that yesterday in the paper presentation, some of his research scholars were there, and all the topics were quite interesting. With this introduction, I would like to hand over the mic to the Professor Sunil Jacob John to deliver his lecture.
Thank you, Professor Datta, for the nice words. I hope I am audible.
Yeah, audible.
Yeah. And on the very outset of this day, that is the National Mathematics Day, very good afternoon to all of you, and my greetings on the National Mathematics Day, the birthday of the Indian mathematician Srinivasa Ramanujan. He was a legend. In fact, I take this as I consider this as a privilege to have with all great mathematicians assembled here, especially Professor Datta. I have earlier we have some occasions to associate and work together, but it doesn't materialize. I hope that we'll get in future. We have some fruitful collaborations, and with that I'll start my session. And I am also thankful to Professor Som. He's a mentor and a friend of our department, especially NIT Calicut, for quite long years. And I will share my slides now. Now the title of the talk is given as Persistent Homology, a tool for topological data analysis. And even though a major part of my work is in soft computing and areas related to fuzzy sets and its generalization, as Professor Datta already mentioned, but what I can say, my initial work was while I was doing in my research work, it was my first love was topology, and I was continuing that, and very recently I have shifted again to this particular area, that is algebraic, particular area of algebraic topology, and there are some students started working in this particular area. So this is coming back to my earlier interest or something like that. Now, topological data analysis, abbreviated as TDA, is a collection of tools, rather powerful tools, that can quantify shape and structure in data. Therefore, that is often a tedious task, how to quantify shape and structure of a data. So this is needed in the domain of the data to answer various questions. Now, how this can be done? This can be done by representing some aspect of the structure of the data as a small topological signature, a nutshell which represents the nature of the data. Now, there are various tools for that, and today's lecture I'm going to introduce one of the most commonly used structure used for this particular technique, that is used for topological data analyzing technique. It is called persistent homology, which represents loops and holes in the space by considering connectivity of the data points for a continuum of values rather than a single fixed value. Of course, many of you may be familiar with the concept in algebraic topology, and especially homology theory and homology groups, homological algebra. All these things are familiar to you, to many of you, maybe many of you. But here we introduce a slightly different one. It is called the persistent homology. From the name itself, it is clear that those natures which are persistent over time will be considered. Those natures, those things which come for a very short span of time and disappears, should be neglected in order to get a better understanding of the data, the structure of the data. That can be done by utilizing the concept called connectivity of the data. Another technique used here is the concept of mapper graph. That is also a similar concept, obviously similar to this persistent homology. Anyway, our interest is in persistent homology, but I am not going for that mapper graph and other things. that can be done sometime, maybe it is another area. Therefore, the problem that we are having is that many of the time we will be having sources of high dimensional data and which are believed to be structured. Therefore, these data are believed to be structured that it is difficult to visualize that. That means in our goal is to extract information or patterns out of this high dimensional data using very fundamental notions of algebraic topology. There are fundamental notions in algebraic topology such as the homology theories. There we have the concept of simplexes and simplicial complexes are there. We will make use of these fundamental ideas so that to extract information out of a very high dimensional data. The problem is that we will identify those signals or small signals or features, and that will be regarded as noise, and that needed to be eliminated from the data, or denoising is needed. And we are interested in those signals which persistent over a long time, which are important as far as data is considered. Now, the problem identified here is that we have a large data set, point cloud, or sometimes that is the fancy name that we are using now. That the problem is that sometimes we don't even know what is the dimension of the space from which the data is coming. It can be one-dimensional, two-dimensional, three-dimensional, etc. That means these points only will be given. The dimension of the space, even the dimension may not be known. In that case, fitting a structure or identify the structure of the data, whether the data is lying in a circle or it is lying in a torus or it is lying in a sphere, it is quite difficult if the dimension is itself is not known. In that sense, what we can do is that we can construct a structure for each dimension. For p equal to 1, for dimension 0, 1, 2, 3, etc. For each dimension, you construct a structure or try to give a particular structure for the data or identify the pattern in the data in assuming that it is lying in dimension 1, 2, 3, etc. That is typically that we are going to do here, and a typical example also will be provided here. So this is the overview. The basic notions of algebraic topology, I assume that we are familiar with that, and some basic definitions together with that. And we see the traditional technique of homology groups and a signature of that often regarded as Betti number. We know that. And these Betti numbers are often used to represent the shape of the data. Maybe it is a parameter which represents the connectivity of the data and the components and how many holes are there, how many voids are there. That is given by Betti number. That's a traditional concept which is available in homology theory. And we will see what is the problem associated with this traditional Betti numbers and how to rectify that. To rectify that, we go to the new concept which we are going to introduce, which is called persistent homology. That's a modification of original homology group, and we'll have persistent homology group. We will define and we'll find the rank of that. And with reference to that, just like the rank of a homology group is defined, Betti numbers are given in terms of that. Similarly, a persistent Betti numbers also will be defined, and based on that, we will identify the structure of the data. And for doing that, we need some filtration. It's a sequence of simplicial complexes, and we'll have the concept of birth and death, and we'll have it can be generalized in a more generalized setup. It can be done with reference to vector spaces and homomorphisms between that. That is called persistent homology module is there. Finally, we will see how it can be represented as a barcode or as a bar diagram, and we'll end up with the references. Now, this is algebraic topology, is one of the most recent branches of mathematics. It is concerned with the identification, description, and discrimination of high-dimensional objects. Now, this, in contrast to more geometrically inclined field of differential geometry, this algebraic topology make use of the connectivity of a space for representing, for finding the structures in data. Now, the thing is that our visualization need to be efficient in the sense that it should be obtainable by reasonable computational means, but also discriminative in the sense that it should permit us to distinguish some form of data from other form of data. This is a compromise, a takeoff between two things. One is computational feasibility, and other one is effective discrimination of the data or structure from one form to other form. That is the compromise is to be done between these two. How this can be managed efficiently. Now, a traditional topology's approach is, we are identifying some intrinsic properties of high-dimensional spaces that do not change under transformations. We know that these are referred as invariants. And obviously, invariants are similar to our visualizations. And to be useful, they need to be efficiently computable and sufficiently discriminated at the same time. That's what I have already mentioned. Efficient computability and sufficient discriminative power. Therefore, a reasonable set of transformations that we may be ignored is the set of affine transformations such as movements and rotation. Therefore, if you have a structure, we have a shape. If you move it from one space to another space, obviously the structure is same. If you rotate it, obviously the structure is same. If you look at from one direction, and you look at it from other direction, obviously the structure is same. Therefore, this can be ignored without any problem. Or in algebraic topology, we ignore even a higher class of operation that we know, that is operations that are described as homeomorphism. All those objects which are homeomorphic are identified as same, and obviously this is unique up to homeomorphism. We'll identify the object. The definition of homeomorphism is given here. I'm not going for that. Obviously, there are objects. A cube can be deformed into a sphere that they are homeomorphic, but cube as well as sphere both are non-homeomorphic with the torus. Therefore, the basic definition is given here. A homeomorphism is a transformation that involves stretching, translation, and bending, but neither cutting nor gluing. It's familiar to we all. It is reasonable to demand that characteristic properties of a space must not change under this type of transformation. Now, sometimes the problem is that this classification up to homeomorphism is not sufficient for us, that is, it seems to be weak, and we need classification among objects which are homeomorphic. That means that is a need when persistent homology is introduced. It is seen that while this method is based on the concept of algebraic topology, it has much higher discriminating power than the techniques of a unique up to homeomorphism, and within that also you can have a classification. That is the importance of this persistent homology. Therefore, this is important, especially in computer science. Also, these are some very basic terms that we are using. Homology is an algebraic method for describing topological feature of data, and persistent homology, it is nothing but a well-developed tool which allows topological analysis on large data sets, where this homology, traditional techniques of homology as well as Betty numbers, fails to capture the actual nature of the data. Here we'll have a more sophisticated techniques called persistent homology. Now, this is a very brief non-expert summary which can be given like this. Now, it is given from a topological perspective only. It is given from a data analyst perspective, or from a computer scientist perspective. It can be different. From a topology perspective, what we input is a filtered complex. I'll come to that. We'll come to that. We'll see what is a filtered complex. And output is a sequence of collections of intervals that is often regarded as a barcode, persistent barcode. And the barcode gives information about homology class, which are born and die as you vary the scale parameter. That is scale. There is a scaling parameter. We represent it as epsilon. And that will be the input will be a filtered complex, and output will be a barcode. And we will see how we will obtain it and how that represent the nature or the structure of the data. Here, what we do here, we have a point cloud as we have seen on the left side, and we cannot analyze points as such like this. What we need is a structure. From this point cloud, we need to go for a topological structure. A space structure should be induced on this point. That the obvious way of doing is that by a neighborhood structure, by defining a neighborhood structure. Therefore, that can be done in many ways. Therefore, obviously, open sets are defined, open balls can be done. Those points which with some radius lying in the same ball can be considered as neighbors, obviously. And most of it is not always necessary that this proximity idea may not be actually taking into account while defining the neighbors. The person who is at the US can be my neighbor, but a person who is sitting very near to may not be my neighbor. If you say that my familiarity or acquaintance with the person as the neighborhood relation. Therefore, what we have is a point cloud. Obviously, a point cloud is a huge data set, still finite, cannot be infinite, but finite set, and we'll join them by a straight line if they are neighbors. Neighborhood relation can be defined in many ways as per the need of the situation. Therefore, we'll have a set, and from that we are going to construct a space out of these points. Therefore, obviously, one topological invariant is the dimension of the space that we are told already that it doesn't have much discriminative power, since obviously we don't even know from where the data is coming. Therefore, for another invariant is what we are going to see, symbolical homology. Here, what we use, the motivation is that we count the number of holes in a topological space as an invariant. Now, for those holes, to identify the holes, we first need a notion of connectivity. For this, we require the topological space being described by a simplicial complex, one of the basic building blocks in algebraic topology. To identify the holes, how many holes are there, how many connected components are there, how many voids are there, based on that only we are going to do this characterization. That means we need something called a symbolical complex, that is a building block in algebraic topology. And these symbolical complex and data structure that explain how to glue together a topological space from the points, sets, triangles, tetrahedra, and their higher dimensional generalization. This is how that means we join points by an edge if they are neighbors. And if 3 points are neighbors, we can fill them a filled triangle. And obviously in 4 dimension, we can go for a tetrahedron, etc. And after that, we glue them together to form a topological space. The simplicial complexes thus serve as the blueprints of a space. The points, edges, and other entities that make up simplicial complex are known as simplices. Therefore, in a graph theory, basically we have the formal definition is there, but we took the combinatorial definition since we want to work effectively with the computers in 1 dimension. Obviously, in 0 dimension, we may think of 0 simplices as vertices, 1 simplices as edges, and 2 simplices are triangular faces, etc. And 3 simplices are nothing but tetrahedrons. And obviously, you can think about the higher dimensional analogs of that and how you patch them together. There are some operations which is possible. We have complexes, we can glue them together, maybe along an edge or maybe along a side or a face. It is possible, but this type of gluing is not possible. This is invalid operation. You can do it either along an edge or a side or a point only. Therefore, gluing them together will get what we are going to get is a symbolical complex. Simplicial complexes are constructed like this. And this is a major theorem that is behind all these things. Anyway, without going too much rigorously defining the terms here, I will just state the theorem behind all these. That is simplicial approximation theorem. Every smooth manifold admits one essentially unique, compatible piecewise linear structure that is equivalent to a combinatorial triangulation. That is often regarded as a simplicial complex. Therefore, from the perspective of computer science, it is important because there are numerous data structures, numerous data structures for storing simplicial complex efficiently, and also the calculation boils down to matrix calculation. That is one of the advantages of this particular one. And in order to do that, what we need is identify these holes. We have to identify the boundaries. Those spaces where there is no boundary is regarded as a hole. And for that, we need a boundary operator. And for that, a formal structure is needed that is called a chain group. And they describe the boundary relation between these simplices of different dimensions. Therefore, when we go from one dimension to other dimension, obviously the connection is through boundary. We first formalize the algebraic structure of simplices within a symbolical complex. Now, this is what we are having. We define a chain group. And members of these are nothing but P simplices connected by obviously boundaries, and also symmetric difference is the operation that we are going to do in this particular abelian group. And the boundary operator will be defined. It's a linear map from one chain group to another group, and we can verify that this is going to be a homomorphism. The chain complex of an n-dimensional symmetrical complex K is the sequence of chain groups connected with the corresponding boundary homomorphisms. So we can see the chain complex here. This is the chain complex that for each dimension that we are having. Construction begins with a chain group CP that we defined earlier, whose elements are nothing but P chains. The chains are nothing but symmetrical complexes connected together. And obviously we have the boundary operator from one chain group of dimension P to P minus 1. And we have a chain groups connected via boundary operators like this. This is called we can write it as a sequence. That is called the chain complex is there. And obviously, I told you that this boundary homomorphism, the boundary is a homomorphism, and you can think about a kernel and image of the boundary homomorphism. And they are nothing but cycle and boundary groups. Therefore, they are also, for every P, the boundaries form a subgroup of the cycles, so that we can take the quotient, which gives the group whose elements are nothing but are classes of homologous cycles. And this is the pth homology group defined as HP for a dimension P. That means the pth homology group is defined as the quotient group of kernel of dou P, the boundary operator dou P to the image of dou P minus 1. This is how the pth homology group is defined. And the algebraic rank of this pth homology group is defined as the Betti number. And this is a short summary of all these things. The Betti numbers are commonly used to distinguish different topological spaces from each other, and it even works regardless of the dimensionality. For example, if you have this is an example of the Betti numbers are given here as a table. And informally, they count the number of holes in different dimensions that occur in an object. We can see that this beta 0 counts the number of connected components, beta 1 counts tunnels, and beta 2 counts voids. And when the space is a point or a circle or a sphere or a torus, we can identify the Betti number beta 0, beta 1, and beta 2 like this. This is given here. Now, as I told that why this is not sufficient. Despite being both computationally insightful, the homology of a complex associated with the point cloud for a particular epsilon, that I mentioned, the epsilon is the parameter that we are using here. I told you that we need some technique. We need some technique to build space out of the points. For that, we will use an epsilon neighborhood system. Obviously, when epsilon changes, the value of the structure, the structure or the complex we are getting out of that will be changing. Therefore, there is no fixed epsilon. And if you can vary that, when you get a different structure. Also in Betti numbers, obviously, we cannot eliminate anything. One requires a means of declaring which holes are essential and which can be safely ignored. That is not given in Betti numbers. The standard topological constructs of homology and homotopy offer no such slack in their stringent rigidity. Here, however, a hole is a hole, no matter how fragile or fine it is. We cannot eliminate small holes which are insignificant or can be considered as noise. It is not possible here. Therefore, that is the reason we are going for this particular structure introduced by Edelsbrunner, Lester, and Samrodian, and that later it is modified by some other persons. And we'll see. This is a parameterized family of spaces whose topological feature which persist over a significant parameter range are to be considered as signal, and with the short-lived features as noises, and that will be short features should be eliminated. And these are some definitions that we will be using here. We have the digital image. All of you know what is a digital image, and point clouds are finite subsets of some ambient space, most often Euclidean. And also shapes are subset of ambient space that satisfy some regularity conditions of one or other kind. And there are two ways of constructing these complexes. One is called the check complex, another one is the RIP complex due to vector S. And this is how we are defining it. Due to shortage of time, I'll be going a little bit faster way, but we have 3 points are there, and if for some epsilon, we constructed a neighborhood nature like this. And if you can see that there is no point common to all the three, but pairwise they are intersecting. Now, if you want to construct these points a complex out of these. These are the given points, and you can see that 3 points are given here, and the area 1. These are the 3 points which are given here, and nothing is there in common. And then what you have in it, if they have pairwise common, if they have non-intersecting part is there, then you can join them by a straight line. And if all the 3 has some points in common, then they will, you can see that there is a 3 points, three neighbors are having a point here, then we will join it by a triangle or a filled triangle. Now the difference is that in the check complex, you can see that here, if you take these 3 points in the check complex, we will join pairwise only. There are pairwise. There is a pairwise common points is there in the neighborhood. We will join them by a by edges. We can see that this is going by edges. And but in the case of RIP complex, what we can do is that if they are pairwise intersecting, then we will join them by a triangle or a filled triangle. Here we can see that the edges are 1-dimensional, these triangles are 2-dimensional, and points are 0-dimensional simplices. And out of this is the way we construct space out of these points. Therefore, from these points, we will construct the space. And obviously, given a real valued function, we can think about T is a mapping real valued function from T to R. T is a topological space. Then we can think about the sublevel sets F inverse minus infinity A. For that sublevel sets, obviously, we'll represent it as TA. Now, certainly, we have the inclusion like T a subset of TB whenever A less than or equal to B. This inclusion induces a map in the homology groups. The inclusion, you know that is usually represented as I star. That's a mapping from HPTA to HPTB, and HP is the homology group of TA as well as TB, and it is given there. And consider a sequence of values A1, A2, decreasing, in fact, A1 less than A2, etc. And corresponding to that, obviously, we can have a sequence like that, HPA1, HPA2, and connected like this, and some mappings are given there and shown as a sequence of homology groups here. This sequence of maps commutes because inclusion satisfies the transitive relation, that is TA1 subset of TA2 subset of TA3 implies TA1 is subset of TA3. Therefore, you can jump from step I to J like this. F of IJP is HPTA to HPTA-J. It is possible for all P where IJ lies between 1 and n. And the homomorphism F takes the homology classes of the sublevel T alpha to those of sublevel sets of TAJ. Therefore, that is there. And the persistent homology group is defined as, based on these maps, which are defined from HP TAI to HP TAJ, we can define the persistent homology group as the image of the homomorphism FPIJ. That is the persistent homology group. And just like the Betti number, here we can have the persistent Betti number as the rank of this particular group. That is denoted as beta IJP. Now, this is what we are having a filtration is having here. Therefore, we start with a point cloud. Obviously, that is obviously sometimes we can start with no point also. We can start with a K naught and then increase the value of the epsilon, so that consider a symmetrical complex K and a function F defined from K to R. We record the function F is monotonic, which means that it satisfies the property. For sigma j subset of sigma, we have F of sigma j subs less than or equal to F of sigma, but this assures that the sublevel sets are subcomplexes of K for every A in R, denoting Ki as F inverse minus infinity AI. Therefore, we can get a sequence like that. You can see that this one, this is your first structure, you go to this one. Therefore, this one is a subset of this one, and this one is a subset of this one. And that way, you will get a filtered sequence. A filtered sequence you will be getting like this. This is constructed by using a value parameter epsilon for a particular diameter. So we'll see an example here. Obviously, the filtrations can be done like this. And we are interested in the homology classes of this, the pth homology class. We said that a class is born at K1 at a stage Ki if the class belongs to the homology group HPKI and but it is not in HPKI-1. That is what we meant by a birth. And a death means Ki merges with a previous class. If it dies entering some Kj, or if it merges with the class which is born earlier, then we will say that is dies. The first value of A for which the whole or topological feature exists is called the birth, and the last value for which it exists is called the death. Anyway, we can see that I told you that this can be done with reference to the vector spaces and linear maps also. It can be done, and we can represent this as a direct sum. That the homology modules can be represented as a direct sums. Anyway, we will see that. I think it will be more clear to you when we take one example, and we will see how these homology groups, persistent homology groups, will be represented in terms of a barcode. If you are having a point cloud here, obviously you can see that there are some hidden patterns here, but obviously if the value of the epsilon is 0, if the value of the epsilon is 0, then if the value of the epsilon is 0, there is no pattern here. Obviously, you can see that now. Now here the points are taken as such. There is no structure which is shown here. Obviously, epsilon is 0. No pattern is here. This is we are going for barcodes in dimension 1. And when we increase the value of epsilon, the parameter value is increased. Here is this along x-axis, the value is increased. And so that, as I mentioned, the value of the epsilon maybe it is a parameter. It can be the diameter of the neighborhood that we are considering. That is about each point. I construct a neighborhood of radius epsilon with for a particular epsilon value, maybe some 4 units, something like that. Still, we cannot have any structure. Any hole is not there. Therefore, we are going for counting connected components, holes, voids, etc. There are no holes are there. Therefore, in one dimension, obviously, we are going to count the number of holes. 0 dimension, we are going for the connected components. In one dimension, we are going for the holes, and in 2 dimension, it will be tunnels, etc. Therefore, here we cannot see any hole, and still we increase the value of epsilon. Again, increase the value of epsilon. The diameter value increased. You can see that. Obviously, you can see some holes are already formed here. Here you can count it down: 1, 2, 3, 4, 5, 6, 7, 8, etc. That means we start a bar at the instant for that particular value of epsilon. If some hole is starting, that we are having a bar starting here, means for this particular value of epsilon, one hole starts. One birth of a hole is happening here, and we extend it till that hole is persistent. Still that hole is persistent. That means again I increase. Obviously, you can see that some holes have disappeared, but some of them are again, some other holes are here. And again, we can think one of the one is that we can count the number of holes here. Obviously, number of holes you can count. You can see that this particular value corresponding this particular value of epsilon, this line cuts the bars at that much number of times equal to the number of holes in the structure, in the space. Again, if you increase, you can see that there are 1, 2, 3, 4. There is a small hole there. 1, 2, 3, 4, 5. There one hole is just taking depth here, and that is there. Again, if I increase again, you can see that there is only one hole. You can see that there is a persistent hole. This is a persistent hole that we can see. Therefore, this is a persistent. These are persistent holes doing for quite a large time. And again, we can say this is also a little bit persistent and it goes for a longer time. Therefore, those holes, these are signals, and others can be eliminated as noises. The small scores, etc., coming here, very minute ones can be eliminated. And this is how a barcode is being constructed. We are starting with a point cloud here, and slowly introducing the neighborhood structure. A topological structure is introduced. By varying epsilon values, you get a barcode like this. Yes, this is a more expanded version of this. We have a diameter here. Again, if you construct diameters like this, this is the neighborhood structure what you are having. And again, we introduce the neighborhood relation via edges, triangles, tetrahedrons, etc. are introduced here. And if you again reduce it, you can see that there are 2 components are here. Here it is only 1 component. Here you can see there are 2 components. And again, if you increase the size of the epsilon, again, all this will become a single component here. You can see here. And this is another example. This way we can see. Again, these bars are also shown there. And finally, I am concluding in 2 minutes. And finally, obviously, I told you that we don't even know from which dimension it is coming. The data is coming from which dimension. It can be from 0 dimension, it can be from 1 dimension or 2 dimension. Therefore, the best idea suited here is that construct a bar for each dimension. Therefore, with reference to H0, the dimension is 0 here, 1 here, 2 here. And these barcodes will represent obviously how many connected components are there. And in dimension 1, and how many holes are there, and or how many tunnels are there, or how many voids are there in dimension 2. In that way, we can count it down. We start with a point like this. Obviously, at here, obviously, all are disconnected in dimension 0. Therefore, all points are standing alone. That means we will be having that much components here. When the increase value of epsilon is increased here, you can see that there are 1, 2, 3, so many components are there. That much number will be this value. This straight line will cut the bars at those much number of times equal to the number of components here. Again, you increase the epsilon value. More nodes getting connected, and there is a filled one is also here. Obviously, you can see there the number of connected components are increased. 1, 2, 3, 4, 5, 6 are there. There were 6 bars are intersected here, and here we have 2 are there. Obviously, 2 holes are coming here. This is a filled one. This color is filled one. This is a hole only. 2 holes are there. There were 2 points that is intersecting. Again, you increase it, and like this. And here also you can see that obviously in this dimension there is going to be 1 tunnel is coming here. Obviously, that is given here. And if you look at the entire pattern, you can see that there is a nature. There is a component that persists over time. In 1 dimension, this is the persistent nature. Now, there is going to be 1 component which persists over time. We are starting with this particular component is always there. Therefore, that will persist over time. And here also you can see there are some voids or some holes which are persistent over time. Therefore, we can take the nature of the data as these ones, and you can simply eliminate all those things which are non-significant, or this can be considered as noises, and that can be eliminated from the data. From this also, this is how we can transform a point cloud into a topological space, and then again transforming it a barcode, and clearly reading the barcode, we can get the nature of the data. We can identify the nature of the data. Therefore, in the interpretation of barcodes, I have already mentioned how that can be interpreted. Where the birth is happening, the bar starts. Where the death happens, the bar ends. And in between, if it persists over a long time, that is a signal. Otherwise, it is a noise. These are the references. And I hope that I concluded in time. I have taken 2-3 minutes more. I'm sorry for that. These are the references, and
Hello.
any questions? You can talk.
Any question, please? Any question? Probably there is.
I have one question.
It's not there. Yes, please, Saurabh.
Is there any application of these things in fractals?
Obviously, in fractals, this is a regularity of the irregular things that we are considering in fractals. What I understand is that, and the concept of connectedness, I don't know how much it is relevant there. And the fractal components, obviously, fractal persistence. Yet too, I have to look into that. I don't know whether it will be applied. It can be applied. Maybe the theory has not developed to that much extent. But hopefully, this is a merging those two may be fruitful.
Thank you, sir.
That's what I hope. Obviously, the dimension we are dealing here is 1, 2, 3, etc. When we go for the fractional dimension, when the dimension lies between 1 and 2, obviously we are not interested. The homology groups are defined for H0, H1, H2. For integer values only it is being done. But if you want to do it for 1.5 or zero point 0.5, obviously it is quite a sensible question. We can think about that. The theory should be developed, can be developed in that direction also. That's what I feel.
Thank you very much.
What I felt really, it was a very wonderful talk by Professor John, and since time was short, he has to run very fast.
So you have given me only 30 minutes. I can try to confine to that one.
Maybe next time we'll try to give you 45 minutes.
Oh,
Anyway,
no worries, sir. No worries. Yeah, thank you, sir. Thank you for giving the
yeah,
opportunity.
you have
Yeah, thank you
done
very
a
much.
wonderful, and the concepts which you have given, these are very, this is particularly this topological data analysis. This is new, this is completely new. And I hope that many new researchers will take this as one of their new areas or research work. So I think that is out of network. His line is there, but anyway, I am thanking both of you, Professor John for his nice talk, and Dr. Datta for chairing the session. Now I invite the paper presentation, because we have our next session as paper